Our team looked at modeling benzene diffusion in water for our concept 1. In our scenario, we are looking at the aftermath of a fire that has degraded PVC pipe and benzene has entered the pipe water system as a solid. We will then be looking at the diffusion of this benzene solid into the water. I'm going to begin with some benzene diffusion general knowledge. First, benzene dissolves into water only slightly and actually floats on top of the water. It also can be dangerous because this benzene is highly flammable. This can be problematic if a river contains a high amount of benzene and it's floating on the surface. It could then potentially catch on fire and is one concern that has to be looked into. Additionally, consuming benzene can cause long-term health effects. Some of these health effects include cancer, blood disorders, excessive bleeding, and damage to the immune system, just to name a few. Additionally, benzene also evaporates quickly into the air. This means that if the drinking water of an individual is not safe and contains benzene, it is not safe to boil this water as it will quickly vaporize and then the individual would then inhale it and could then still suffer from some of the long-term health effects. In our scenario, we had to make some assumptions for the model. The first assumption that we made is that we assumed that there was a forest fire that decomposes the PVC into benzene as a solid that's in the water. After this, we then assume that the temperature drops down to 60 degrees Celsius immediately after, and it remains constant for the duration of our modeling process. Another assumption that is made is that the water in the pipes are stagnant when the benzene is diffusing into the water. This means that the system can be treated as a batch reactor. Additionally, we will be using a 3-inch diameter PVC pipe, and we also looked at 100 feet in length of the pipe. We used a 3-inch in diameter PVC pipe as we found this was the most common for drinking water pipes that were in homes. Additionally, when talking about the area in our calculations, the area is the internal cross-sectional area of the PVC pipe and is then looked at across the entire length of the pipe. The one resistance model for benzene diffusion is shown on the right, where the blue is the water interface and the red is the benzene interface. It can be seen on the right that the concentration of water at the interface is very similar to the concentration of water in the bulk phase, and this is because the rate constant for water is much higher than the rate constant is for benzene, and that's why you see the difference in the concentration of benzene at bulk and the concentration of benzene at the interface. And that's because this is the limiting factor and is being modeled in this. Additionally, this system is being modeled as a closed system due to water being stagnant, and this is important for the future calculations. From the one resistance model, we were then able to find the ODE for this model. On the right, you can see the derivation for the ODE for this problem, and it's important to note that the delta C is derived from the concentration profile at the interface. This means that the delta C is going to be the concentration at saturation minus the concentration at any given time. The driving force for this equation is how far away the system is from the saturation concentration. If the concentration at a given time t is very close to the saturation constant, then the dC over dt, the change in concentration, is going to be very low. When the concentration equals the saturation concentration, then there is no longer a change in concentration for this system. From the ODE, we can then find the analytical solution. The analytical solution is important in order to compare with our MATLAB modeling to ensure that the data is accurate. The way that we found the analytical solution was first we reduced the terms that were constant into smaller constants, such as condensing the Ka over V value into alpha and the alpha times C saturation into beta. After we did this, we separated the terms to get dC on one side and dt on the other side. And from here, we used U sub technique in order to find the integral of each side of the equation. And we're then able to find what the integral of that was. From the final step that is shown in the screenshot, we can then start substituting the alpha value and beta values for their constant terms and solve for the equation. This is not done complete in this video, as it is part of the quiz, and the full solution can be found on the quiz 1 of concept 1. Some of the challenges that we faced in modeling the diffusion of benzene is 1. Finding a reliable rate constant with correct units. We found that the volatilization of benzene was a much more studied topic than the diffusion of benzene in water, and because of this, it took us a lot longer to find a rate constant with the correct units, and that made sense. We ended up having to model a few rate constants that we found and determined which one made sense in terms of our model. Additionally, another problem we ran into was determining the amount of benzene that was being released from the degrading PVC pipe. We originally wanted to model the PVC pipe degrading and releasing a certain amount of benzene over time, and then that benzene at the same time being diffused into the water. This was something that we were not unable to do, and because of this, we made the assumption that the forest fire came through and degraded all of the PVC pipe, and our modeling started once there was already benzene in the water, so we can then model the diffusion of this benzene into the water system. Finally, an additional challenge that we ran into was calculating the change in concentration of benzene during the fire. The reason that this was so challenging and was something that we did not go through with was because there's very little information about the rate constant of benzene at high temperatures. To get around this challenge, we made the assumption that the forest fire came through, and then after the forest fire, the temperatures of this system reached 60 degrees Celsius, and we modeled the diffusion of benzene at this 60 degrees. Finally, we will be looking at the applications of benzene diffusion modeling in the real world. First, benzene concentrations in rivers downstream of a crude oil spill can be modeled via benzene diffusion modeling. This is important as one example is in the Yellowstone River, there was benzene found in the river due to a crude oil spill, and this would be slightly different than our model, as there are two main factors that we do not account for that modeling in a river would have to. One is that the water is not stagnant and it is constantly moving, and this would add an additional complexity to the modeling, as well as the surface of the water is open to the air, so there will have to be modeling for the volatilization of benzene as diffusion is happening as well. Another application can be for finding the benzene concentration in drinking water from PVC pipes. This is very similar to the modeling that we are doing in our scenario. However, in the drinking water, you would have to assume that the water in the pipes are flowing. And the reason that this would be really important is because of the adverse health effects that benzene has. If there are health effects of consuming large concentrations of benzene, finding what the concentration at the tap would be very important in ensuring the safety of a community, and also if the benzene concentrations are higher, then sending out proper guidelines on how for individuals to consume safe water would be important for that community. Finally, another application could be finding the benzene concentrations in a lake that where benzene has flown in from rivers. So once the benzene is in a lake, it is much more, or it acts much more like a batch reactor, similar to ours. However, it's similar to the instance of a river. The surface is open to the air, so you will also have to model the volatilization of benzene at the same time as the diffusion of it. This would be important to find for a number of reasons, some of them being finding the ecosystem health and finding any health effects that could be happening to species that live in this aquatic ecosystem, as well as finding the potential harm that could come from humans entering the lake and swimming in it if they were to consume any of this benzene. The assumptions that we have made in this model have been referenced from the sources below, as well as these are the sources that we have found some of the rate constants that we've been using in the MATLAB for our calculations.